Namaste. Today in this video we are going to discuss about informed search. Okay, in previous video we have discussed about uninformed search. Okay, so let us discuss about informed search. Informed search is also termed as heuristic search. H-E-U-R-S-T. Okay, heuristic search, because it uses information about the domain to reach the goal, and there is information about the direction to reach the goal. Okay, in uninformed search it does not use the knowledge and the direction, yes, but in informed search it uses information and knowledge to reach the goal, so it is informed search. Okay, so let us consider the types of informed search. Best first search. Okay, next one is A** search. Next one is hill climbing. Next one is genetic algorithm, and etc. Okay, so we will be discussing these four types of searching approach used in informed search. So let us consider first best first search. Not best first. Okay, and it is aggregated form is BEFS. Okay, if BFS is only written, then that is called breadth first search. If BFS, then it is best first search. Okay, so let us discuss about best first search. It is also known as greedy best first search. Okay, because it choose the cost node with less cost. Okay, greedy approach, that means so greedy best first search, and it uses heuristic function. Okay, it uses heuristic function that is represented as Hn, and it is normally termed as the path cost or straight distance cost from the goal node. Okay, Hn is the cost or path cost or straight distance cost from goal node. So Fn is equals to, that is Fn is equals to Hn. Okay, so we are discussing about the performance parameter. Okay, performance measure parameter. So complete, the BFS is not complete. Okay, completeness is no, as it can stuck in the loop of the given tree or given searching tree. Time complexity. Okay, time complexity is big O notation of B power m. Okay, and it can be decreased or improved if it uses proper heuristic function. Similarly, space complexity. Okay, space complexity is also big O notation of B power m. And optimality, it does not provide optimal solution. Okay, and it tries to expand the node that is close to the goal. Okay, it tries to expand the node that is close to the goal. It sorts the queue according to heuristic function. Every time it sorts the queue of a node according to heuristic function. Okay, so let us consider an example. Okay, okay, A, B, C, D, okay, E is here, E, F, G, okay, H, I, okay, let it be here. So let our goal node be I and starting node be A, okay, and node to node distance is 100, okay, 80, 120, 150, okay, 105. Here it's 60, 70, 80, 30 and 50. This is only the assumption, okay. We can consider any example and let the node and HN, that means distance from the goal node. So A, B, C, D, E, F, G, H, I. This HN is calculated as straight distance, okay. So D to I, B to I, F to I, S to I, G to I, these are straight distance cost, okay, that is HN. So let it be from A, let it be 350, similarly from B 320, from C 310, from D 280, from E 250, from F 200, from G 180, from H let it be 80, and I is a goal node, so goal node to goal node distance is 0. So let us consider this example and solve it by using best first search, okay. So step 1, so we start with node A. Since it is a single node, so we choose A, so it is by default choosing A. So step 2, okay, so A is explored and its child node as B, A, E and C, yes. So B, E and C. So the straight distance cost from B is 320 and E is 250, okay, and C is 310. So here the distance from goal node, E to goal node is less, yes, so we choose E node. That means HN of node E is less than that of HN of B and C. So that is HNE is less than HNB and HNE is less than HNC. So we choose next E node as E, okay. So again we explore node E. So we have gone to A, yes, and now we go to E. So when we explore E, we get F and G, okay. So the HN of F is 200 and that of G is 180, yes. So the smaller part is, smallest value is 180. So HN of G is, okay, write it also, G is less than HN of F, that is HGN is less than HFN. So we choose node G, yes. So step 4, okay, again we explore A it is E, not E. Okay, E, F, G. So we have choose G. Yes, so this is not written. Okay, sorry. So G. So G is explored with I. Yes, in this way I, and I is the goal node. So we have reached the goal node. Yes. So we have the path A to E, E to G, and G to I. Yes. And what will be the total path cost? That is summation Hn. Okay. So Hn means, what is the value of summation of Hn? We move from A to E, E to G, G to I. Yes. So we add from E. Okay. Not from A. Also we can add from A. Okay. That is 350 distance. But we move from A to E first, and E to G, and G to I. Okay. So let it add HA plus HE plus HG plus HI, and we get the value, that is total path cost. Okay. Next one is total distance cost. Okay. So this is summation Gn, that is G. Okay. What is the value of G? We get from A to ES, that's A to E is GAE plus, and we go from E to GS, E to G, E to G, that means G, E, G plus, and from G to I, G, G, I. So we get total distance cost. And so total cost is now summation Hn plus summation Gn. So this is how we get the solution of this graph by using best first search. Okay. Now let us move to the asterisk search. Okay, we will be considering same example. It will be easier for us. So asterisk search. Okay. So asterisk search, it avoids expanding the node that are already explored. Okay, and it uses heuristic function as well as node to node distance. So that is Fn is equals to Hn plus Gn. Okay, so this is the most necessary part for the asterisk search. Let us consider the measurement parameter. Okay, completeness. Yes, it is complete because it combines the property of both best first search and uniform cost search. Okay. Time complexity. It is exponential. Okay. And space complexity. It is also exponential. Okay. And optimality, or optimal or not, it is optimal because it combines the property of both uniform cost search and best first search. Okay. So let us do the same example. Okay. So step 1. Step 1 is similar as like best first search. Step 2. Okay, here is different. Okay, so A, we go to B, C, sorry, E and C. So in previous case, in best first search, we use 320 here, yes, but in this case we have to use HN and GN both. So the value of HN is 320 plus, and A to B distance is 100, so we have to add 100. Similarly for E, 250 plus 120. Okay, similarly for C, 310 plus 105. Okay, now that is equals to 420, that is equals to 370, that is equals to 415. So here Gn, okay, I am writing here, Gn of E is less than that of Gn of, okay, Gn of B and C. So, or that is, okay, Gn E is less than Gn B and Gn E is less than Gn C. So we choose node E. Okay, so again we explore it. Okay, node E is explored. So step 3, A to E, and E is explored to F and G. So what is the HN of F? It is 200, and GN is 60. Okay, and for G, it is HN is 180 plus, and GN is 70. So it is 260, it is 250. So again smaller part is G. Yes, so since Gn of G is less than that of Gn of F, that is, okay, Gn of G means Gn is less than Gnf. So we choose G. Okay, so again we explore G. That is step 4. A, E, G. Okay, and I. So we reach here goal node, and Gn becomes, what is the value of I, Gn of I? It is 0 plus distance is 50. So it is 50 and only single node. So we reach the goal node, and the part is A to E to G to I. And similarly we calculate the part cost, total distance cost, and total cost as previous. Okay, so in this way we have solved the best first search and asterisk search, or we have used best first search and asterisk search to solve the given searching problem, to search the goal. In next video we will be discussing about genetic algorithm and hill climbing approach. Okay, thank you and bye bye.